Welcome back, engineers. We are discussing common techniques and algorithms in system design, and in one of the previous videos we discussed quad trees. We saw the theoretical understanding of it, and I promised you that I'm going to give you some code implementations and demos. So in this video, let's have a look at a little demo about how quad trees work. We'll actually pick up a point randomly on Google Maps and see how quad trees actually work, and we'll see the code implementation as well. I hope you're ready. Let's get started. So before we go into the demo, let's have a quick recap about what are quad trees. So quad tree is one of the data structures used in spatial search and image processing and gaming kind of applications. So it's basically a breakdown of an entire 2D plane into different smaller parts like quadrants. So whenever we want to do any proximity kind of search, so we go from the top down, we go from the entire world view into the respective quadrant where our point of search lies, and from there we're going to find the nearby locations or nearby drivers or riders or restaurants, whatever it may be. And that was the main idea behind quad trees. So before we go into the code, I have actually put together a little UI demo for us so that we can actually see and play around with a quad tree implementation, right? So let me start the server. So this is a simple FastAPI server running on the back end, and on the front end there's a simple HTML file, and this is what we have. It's a simple HTML with basic styling from Bootstrap. So this is our quad tree implementation. So let's say if we are visualizing the current state of quad tree, there are no points in this quad tree, right? And it's not divided as well, right? So there are no subchildren or subquadrants. Okay, so what we'll do is we will keep inserting certain points. So I've identified some key areas in Hyderabad which are like prime locations, and if I hover over them, you can see that there is one point here. Have a look at the map. There's a Charminar, there is a high-tech city point, there is Gachibowli point, and there is Secunderabad railway station, right? So there are different points spread across the city. If you don't know the lay of the city, that's perfectly all right. Just think of it as a 2D plane, and there are a few points. So let's say there are a few drivers that are available in the city at these different locations, right? So there are 5 different drivers spread across different city, and we are going to pick a random location from the city, and we'll see how we can actually get the nearby drivers, right? For example, if I'm picking somewhere here randomly, I'm expecting to see only this driver, but when I'm picking something randomly here, I'm expecting to see multiple drivers pop up on my screen, right? So here is how it goes. So these are different drivers, right? Which means they have different lat longs. So we're going to insert these lat longs into our quad tree so that they act as our current positions of the drivers, let's say. So we're going to use this UI using the insert API. We're going to give latitude, longitude, and an optional label, and we're going to insert it into the quad tree. And once we have all these drivers in the system, we're going to do a search. We're going to pick a random point from the city from Google Map, and we're going to actually do a search, and we will visualize how the quad tree is looking like after insert, and we're going to see what are the search results available, right? So let's see. So I've identified these points, and in the readme file all these points are already given to you, so you can play around with them. And if you're in a different city, you want to play around with your own lat longs, identify key landmarks and just put them in the quad tree, right? So let me begin by taking the latitude and longitude of the first location, which is Charminar. So this is how we can insert it: longitude, latitude, and the label. I just added the label for us to see easily when the results come out. Instead of just checking on lat long, we can actually identify using labels. So our first node is inserted into the quad tree. So if we visualize the quad tree right now, we can see that there is a point added into the quad tree, right? So right now there is no subdivision because I have kept the capacity to divide at 4. So if there are more than 4 nodes given into a particular quadrant, it breaks down into subchildren. Okay, so I'm going to quickly add these points and see you in a bit. Okay, so I've added the 5 different points which we have identified in the map, which are our current positions of our drivers. So when I say visualize a quad tree, now we can see that there are 4 nodes available at the root level, and when I have added the 5th node, it divided into 4 different quadrants. So these are the children: northeast, northwest, southeast, and southwest, and the 5th point got added to the southeast boundary, right? So this is where our railway station is, and if you look at the map, this is the farthest point here. So this is the one that I've added at the end, so that's why this is the child that's been subdivided. Okay, so this is our layout. So what we'll do now is we'll pick a random location. So let's pick a location from here. So let's say I am picking some location here randomly, and this is the lat long for it. I'm going to give it into the search API like this. So this is the longitude. I'm going to cut the latitude. I'm going to give the latitude here, and this is the width that we are searching for, width and height. So this is kind of giving us a range of about 10 kilometers, and we are trying to get the drivers available in this range. Okay, we are getting High-Tech City and Gachibowli, which is what I expected, because a couple of our drivers were here, right? High-Tech City and Gachibowli, very nearby location, but we have not gotten the results from this side of the area, right? So let's pick something from here. Let's say we are picking Snow World. Let me take the lat long of Snow World, and what I'm expecting is to get the drivers from that region. So I'll do the same thing. I'll copy the latitude and longitude here, and I'll hit search. Okay, this time we are getting Secunderabad railway station, which is correct. So if you increase the search radius, let's say we're not finding any drivers and we want to look beyond our search scope, so we can increase it. Let's say from 0.05 I'm going for 0.1, which is giving me about 20 kilometers, let's say, approximately. So now if you see, we get 4 drivers, Charminar, Golconda Fort, High-Tech City and Secunderabad, but we have not gotten the farthest driver from Secunderabad, which is Gachibowli, right? So if you go beyond it, let's say I'm giving 0.2, which is a very big radius. Now I'm getting all the 5 drivers, right? So this is how a quad-tree implementation typically works. Okay, so this is a simple UI, which is just a wrapper of APIs to interact with the quad-tree implementation. So you can play around with it, give your own CT lat longs, identify drivers or riders or restaurants, whatever you want to do with this quad-tree implementation, right? So you can do insert, you can do search, you can also do delete if you've accidentally inserted something, or if you want to play around with delete as well, right? So all the APIs are already given to you. Now let's look at the code. So on the folder level, this is a quad-tree implementation which has 2 folders, Frontend and Backend. In the Backend, there is a simple file called code.py, which is where our data structure is lying. And then we have the server.py, which is our FastAPI, basically where there are endpoints for our CRUD operations, right? And the required libraries are available here for you to install. And there is a README inside Backend folder. You can go through this README to understand how to set it up, what to install and how to run it. I've already given the examples for Hyderabad with lat longs. You already have the curls. If you want to test this in Postman instead of the UI, you can do all that stuff here. Okay, and on the front end side, there is only one file, which is index.html, which is a simple HTML with basic styling. So if we look at the header, we have Bootstrap for our style sheet, and then we just have basic HTML and JavaScript, right? So basically we have a quad-tree section, visualize section, insert section, search section and delete section, and this is the JavaScript side of it. So we're just making API calls and rendering them on the UI. Okay, so simple stuff on the front end. Now let's look at our quad.py, right? So if you remember the structure of a quad-tree node, we've discussed it earlier in the video. So it looks something like this. So there is a center point given and we are giving a width and height. So this will act as our rectangle. And then we have 4 children, top left, top right, bottom left, bottom right, also known as northeast, southeast, southwest and northwest, right? So we have the children, and then we have a Boolean identifier to identify whether this is a leaf node. So this is the high level idea about what a quad-tree node should look like, and when we actually implement the code, it looks something like this. Okay, so first we have a point class, which is just having a latitude and longitude, and I have added an additional label for our ease of use, right? So this is the first class called point. Okay, and the second class is a rectangle class, which is taking the center x and y and width and height. Okay, this gives us a rectangle. We take both of these points into our quad-tree node. So if you look at the init, which is basically a constructor in Python, so what we'll do is you're going to give rectangle, which is having a center point and width and height, and we are also going to give a capacity. Capacity is the criteria that will define when the subdivision should happen, right? So this is how it looks like. In the initializer, we are just giving it a boundary, a capacity, and initializing our points to empty list, and this is not divided. and we have 4 children which are pointing to none. Okay, so this is our initializer. And now let's look at our 4 APIs. So this is the insert algorithm. What is the insert doing? If the point is not within the quadrant boundary, it cannot be inserted here. So this is a basic check. So if the node has capacity, add the point directly. This is our second check. If there is within the capacity, we're going to append it to our points. Okay. And if it is exceeding the capacity, this is where we're going to do the recursive subdivision, right? Subdivide. So if not self-divided, we call the subdivide method, which is simply doing this piece, divides a quadri node into 4 smaller quadri nodes. So it's basically creating a new rectangle and then assigning 4 quadri nodes based on the calculations of these 4 rectangles, 4 quadrants basically, and marking it as divided. Okay. And what else? I think that's it for insert actually. So let me close insert. Now let's see how search is working. So this is how the query algorithm goes. So we are going to give it a range to search for, and if there are any nodes available within that range, we're going to add them to our collection. Otherwise, we're going to check if it is divided. If it is divided, we're going to go into each of the quadrant and repeat the same query operation for all the quadrants, right? So since we're doing a query call again, this is a recursion, and if there are further sub children for any of the quadrants, it's going to do the same thing again, right? So that's how we're going to collect our points. So the next one is delete, and this is how delete operation goes. We're going to take in a point which is xy coordinate. We're going to search within our rectangle. If the point is found, we're going to pop it, and if it has any further sub children, we're going to pop those as well using recursive delete calls. And if there are no children, we are actually going to merge it into the parent. Okay, so simple algorithm. So this is how it goes. So we're going to check in our self.points, which is having all the points in the current quadrant. So if there is a match, we're going to simply pop it out of it, and once we pop it, we're going to check if there are any empty children. If all of them are empty, we're going to just collapse the children. Otherwise, we're going to check if this is having any further subdivision. If it is true, we're going to call delete on all of those quadrants, right? And that's how delete algorithm goes, and the rest of them are simple helper methods for us to work with. Okay, so this is how the entire quadri implementation looks like. So definitely check it out. The code is available on GitHub. So if you're wanting to explore, just fork it, clone it, whatever you want to do, explore it on your own, and let me know if you have any doubts, right? Thank you so much for watching, guys. That's it I had for this video. Please leave a like if you found this helpful. Please subscribe if you haven't done already. I will see you in the next one. Cheers.